Hi, my name is David Nataf. I'm a graduate student at the Ohio State University Department of Astronomy. In this video abstract, I briefly summarized the results of our recent paper, The Reddening and Extinction Toward the Galactic Bulge from OGLE-III, the inner Milky Way's RV of 2.5 extinction curve. In this work, we apply the red clump method to OGLE-III observations in order to measure the reddening law, the differential reddening, the extinction, the mean distance modulus, the dispersion in distance modulus, and the relative number counts towards 9,000 bulge sightlines spanning 100 square degrees. We find that the reddening law toward the inner galaxy goes as an RV of 2.5 extinction curve rather than the standard RV of 3.1 extinction curve measured for the local interstellar medium. Before moving forward, I will acknowledge the spectacular OGLE-III Galactic Bulge photometric survey. The survey measured the photometry of stars over 100 square degrees of the bulge in V and I down to 20th magnitude. In this figure, I show the parts of the survey used in this work in red superimposed on an optical image of the bulge. I then show the 1.3 meter Warsaw telescope at the Las Campanas Observatory operated by the Carnegie Institution for Science. The deep V and I photometry allow us to accurately measure the properties of the red clump, the horizontal branch, of the bulge nearly everywhere in the survey. Figure 3 on the left shows how we can accurately measure the number counts and magnitude dispersion as a function of direction. On the right, in Figure 2, we can clearly see that differences in extinction affects the observed color and magnitude of the red clump. Two sightlines near one another have red clumps that differ by 1.44 mag in I and 1.17 mag in V-I. If we are to infer distances, we must determine both the reddening and the reddening. Inferring distances would be a straightforward task if there were a single extinction law. Unfortunately, as we see in Figure 11, the extinction law is a steeply sensitive function of direction. A regression of the scatter to the V-I and I of red clump centroids yields very different extinction laws over the reddening interval that is scoped. For these two sightlines, which are at the same longitude, we measure a 24% change in the reddening law. To further complicate matters, we cannot know if the extinction curve extrapolates back to zero reddening. In the top right, we show Figure 5, our reddening measurements. We cannot convert these to extinctions without knowing the extinction curve. To resolve this puzzle, we combine optical reddening measurements from OGLE-III data with published infrared reddening measurements from VVV data. The ratio of infrared to optical reddening, shown in Figure 12 in the bottom left, can be used to yield a distance-independent estimate of the properties of the dust, and thus the extinction curve. We derive equation 28, shown on the right, which yields a total to selective extinction ratio in V and I as a function of the reddening in V minus I and the reddening in J minus K. Our solution for the extinction allows us to infer the mean distances to bulge stars as a function of sightline. On the left, I show Figure 17, from which the galactic bar is clearly discernible, modulo some projection effects that distort the apparent bar. These projection effects, or rather the structural parameters of the Milky Way's bar that create them, are open, unsolved problems of astrophysics. On the right, we show Figure 20, the relative surface density of bulge stars in the top panel, and dispersion and distance modulus in the bottom panel. It is our hope that these measurements of these structural parameters and the full error matrix thereof could help other researchers can determine the morphology of the bar. I hope you've enjoyed listening to this video abstract of my recent paper. I believe that we've made strong progress on several issues, notably the extinction curve towards the inner galaxy and the parameters of the galactic bar. However, at this point, there are many more questions and answers. For example, the extinction curve that we find, with an RV of approximately 2.5, is very similar to the extinction curve that has been inferred towards a host of Type 1a supernova and extragalactic observations. Is this similarity a coincidence, or is this due to underlying similarity in the environmental conditions? We're not sure, but it could be an avenue of future research. Further, the parameters of the bar that we measure are strongly suggestive of an X shape superimposed on a bar. Is that all there is, or is there more? That would require detailed modeling to figure out. If you'd like to know more about these results and the methodology used to derive them, I hope you read my paper posted on astro-ph and submit it to the Astrophysical Journal. Thank you.